Okay, so demonstration by mathematical induction. So it's a very powerful demonstration technique. Right, I think it's better to deal with it with an example. It's a three-step process. There is step 1, then 2, and 3. And let's do that with an example. We want to demonstrate that if I add 1 plus 2 plus 3 plus up to the value of n, well, this would be the same than doing n times n plus 1 over 2, and that we want to show that this is valid for all n belonging to z, n greater or equal to 1. Okay, so step 1. Let's prove the statement is true for n equal 1. So for n equal 1, well, the left-hand side is just equal to 1, because only one term, whereas the right-hand side would be equal to 1 times 1 plus 1 over 2, which is equal to 2 over 2, which is equal to 1. Yeah, so that it works. So that's equal to the left-hand side. So it works for n equal 1. Now, step 2. Now, we assume that 1 plus 2 plus plus n equal n times n plus 1 over 2 is true for n equal k. So that means that i.e. 1 plus 2 plus plus k is equal to k times k plus 1 over 2. And now, with this assumption, it's only an assumption, we don't know yet if it's true or not. We have assumed it's true. Let's prove that if it's true for k, then it's also true for k plus 1. Okay. So, recap. Assumption 1 plus 2 plus 3 plus plus k is equal to k times k plus 1 over 2. Okay, so for k plus 1, the left-hand side would be 1 plus 2 plus 3 plus plus k, and then there is another term, which is k plus 1. Now, we can use the assumption to say that this is equal to k times k plus 1 over 2 using the assumption, our assumption. So therefore, the left-hand side is equal to k times k plus 1 over 2 plus k plus 1. Now, okay, so I can simplify that. It's two fractions, so it's k, the common denominator is 2, k plus 1 plus 2 times k plus 1 over 2, which is, okay, we can factorize by k plus 1 the numerator. So k plus 1 times k plus 2 over 2. Oh wow, here we go. We can see that basically this formula is the same than our assumption, but for k plus 1. So the formula is true. Is true for k plus 1 if it's true for k. Now step 3, we bring all of that together in a conclusion. We know the formula is true for n equal 1. That's what we did at step 1, okay? We also know the formula is true for k plus 1 if it's true for k. So therefore, well, if it's true for n equal 1, well, therefore it must be true for n equal 2. So therefore it must be true for n equal 3. And therefore it must be true for n equal 4. And therefore for n equal 5. And so on and so on. Therefore, by mathematical induction, the formula is true for all n greater or equal to 1. Let's do another example. Prove by induction the formula one square plus 2 square plus 3 square plus plus n square is equal to n times n plus 1 times 2n plus 1 over 6. Okay, so step 1, again, always 3 step. For n equal 1, well, so the left hand side is just 1 square, which is 1, whereas the right hand side is equal to 1 times 1 plus 1 times 2 times 1 plus 1 over 6, which is so 2 times 3, so that's 6 over 6, which is 1. Yes, that's also true. So therefore, yes, the left-hand side is equal to the right-hand side. Right, so it's true for n equal 1. Now, step 2. We assume it's true for k, i.e. 1 square plus 2 square plus plus k square is equal to k times k plus 1 times 2k plus 1 over 6. Now, in that case, for k plus 1, the left-hand side is equal to 1 square plus 2 square plus plus k square plus k plus 1 square. This, using our assumption, is equal to k times k plus 1 times 2k plus 1 over 6. So I'm just going to say using our assumption. Okay, so therefore the left hand side is equal to k times k plus 1 times 2k plus 1 over 6 plus k plus 1 square. Okay, so we can simplify that by factorizing by k plus 1. So it's k plus 1, and then, okay, so we just 6 over 6. So k plus 1 times k times 2k plus 1 plus 6k plus 1 over 6. Okay, so that means that the left hand side is equal to k plus 1 over 6, and then inside the bracket we have what? 2k square, then plus k plus 6k, so that's plus 7k, plus 6. Now, if we are a bit clever, we can see that it's equal to the roots of this are k plus 2, and then what, 2k plus 3, which I can rewrite as k plus 1, k plus 2, 2k plus 1 plus 1 over 6, which is the same formula as the formula above, you know, but applied to same formula than this formula here, but 4k plus 1. So therefore, it's true for k plus 1 if it's true for k. And then step 3. Alright, that's the conclusion. True for k equal 1. True for k plus 1 if true for k. Therefore, by mathematical induction, the formula is true for all n greater or equal to 1. And I think I'm going to stop with this last example.